Hi, today we're going to cover induction. This is very important method. Induction can prove some logic and natural number. Uh, if there is a rule uh, which can be true for all natural number, we can use induction instead of either proof method. Okay, before start induction, I'm going to review last class. We have discussed about number theory. So this is basically study of integers. We have discussed about divisibility of theory, and we have seen division algorithm, and we have seen prime number related algorithms. So yeah, primality is important. So an integer p is prime if its only divisor are 1 and p, that is prime number. So if there is a positive integer and this number is greater than 1 and not prime, that is a composite number. So let's look at some fundamental theory of arithmetic. And this is show how to make this composite number using prime numbers. Every positive integer greater than 1 has a unique prime factorization. Here is the example. 48 has 2 multiply and 2 multiply and multiply 2 again multiply 3. So we have 2 to the fourth multiplied by 3. That gives you 48. And other composite number has their own unique prime factorization. We have seen this Euclid theorem. This one gives you some infinite number of primes. So we can prove this using contradiction. Suppose there are a finite number of prime, p1 to the pn. So we can define a set p, a number p, that is p1 multiplies, p2 multiplies, p3 multiplies, and go up to pn. And we can set another number q that is p plus 1. The first case, q is prime, then q is a prime different from all of p1 to through the pn because that is greater than them. And case 2, q is greater than 1 and it's not a prime. Then q has some prime factor p, and which must be in the list, and therefore p is a divisor of large p, and p also the divisor of large q. So that means p is a divisor of q minus p, which means p is a divisor of 1. So both cases are contradictions. So the assumption is false. That means there are an infinite number of primes. So we also have discussed about these two famous algorithms. The one is primarily testing, another one is factoring. Primarily testing gives you a random number, an integer n is prime or not. The factoring gives you the prime factorization of the number. Basically, factoring is very expensive because you have to compare all possible prime number from 2 to the maximum prime number can be applied to the composite number. And using that, we can make this we can find greatest common divisor from two integer. What is that? If there are two integer a and b, we can find a largest integer d such that d is the divisor of a and d is the divisor of b. So if we have 100 and 125, 25 is the greatest common divisor of that. So we can find that using factoring, because if you have this final factorization, so you can see what is the common through the prime factors. So there is prime number with how many times that used for this number. For A, we have 3, 2, 1, 3, 2, 5, 7, and 11. They are one time. So B has a different number of prime numbers, but it has 2, 3, 5, 7, 13. It doesn't have 11. So we don't have 11s, that will be 0. We don't have 13, that will be 0 again. Here, we can read them in this hazy. So let's look at it. So A has 3 for 2, B has 1 for 2, and other prime numbers are same way. So for that, we need to find a common number. So if we find this small number of those two, that is the smallest number. That is the combination of greatest common divisor. But factoring is expensive, so we need to compute this without factoring. That will be much more applicable. So we can use the Euclid algorithm up there. And yeah, this is GCD of A and B. That will be converted to GCD B and modified B. So we can repeat this modification until the second part will be 0. In that case, we'll get, in this case, A will be the last answer. So using this algorithm, we can find the greatest common divisor. So here is the example, and we have GCD of 660 and 126. So 660 is greater. We can convert using that property. So now 660 will be 30 if we keep trying same conversion onto that. We will get GCD 6 and 0. That means the GCD is 6. So we can simply write down this in tabular form over here. 660, we have 126, and the remainder will be 30. 30 we can write down this number using 30 again, and remainder will be 6. Here we can make this 30 using this remainder, and the last remainder is 0. That means the GCD is 6. So we can extend this algorithm to this, and this will be used in the encryption. And here is the important thing. If you have large enough two prime number, we can multiply them together. How to find their prime number factorization? It is really difficult to find. So using this, we can make very strong encryption. So when you want use encryption, you may need a key. So for the perfect encryption, Alice and Bob need to share a secret key. So if they want to uh, talk with this encrypted message, they need to prepare a message first and make this encryption using this equation and then send to another. So Bob received the message that is encrypted message. And Bob want to read that. Yeah, there is way to decryption method. So in this case, the encryption is good, but they need to keep the same key in the secure location. But it is very difficult. So that's why there is a better method, the public key cryptography. In this case, both parties need to keep their private key in their secured position. Then they can share the public key to decrypt the encrypted message. In this, the RSA is the most famous method for this. Rebest, Shamir, Derman invented this method. It used that multiplication, big, large primes. So anyway, they need to make this large prime number combination and find public key, private key, and share their message, share their public key, share their message. They can encrypt, decrypt their message in the very safe way. Yeah, this is the details of that. So we have discussed about primality. One of them is Euclid theorem, and another one is factorization, primary testing. We have discussed about greatest common divisor. It requires factoring, but that is really expensive. So that's why we can use other methods to find GCD without factorization. And with this prime number, we can use public key cryptography. That's it. Yeah, let's move on to yeah, let's move on to today's topic, induction. So, what is the mathematical induction? Uh, yeah, mathematical induction is a method for proving statement about all natural numbers. So, uh, yeah, there is a rule, a new logical inference rule. It only applies over natural numbers. The idea is to use the spatial structure of the vectors to prove things more easily. Particularly, this is very useful for reasoning about program. Here is an example. We have for loop. We want to show how it is work. So we can show pi hold after I times through the loop. So, so there will be a function in the for loop body that is always same, but it gives a different result at each iteration. And here is a function as well, which can produce Fibonacci number. So f of x is equal to x for all value of x is greater than equal to 0, which rule is shown by induction. Okay, let's look at this example. Okay, when a is odd number, a to the nth is odd. Okay, how to prove this? Let's try contrapositive. If the n is the arbitrary number and greater than 0, suppose that n is odd, we know that if a and b are odd, then a times b is also odd. So let's try. We can multiply a n times. Okay, a multiply a, that should be n to the nth. So yeah, how to show all the proof of n is it could be infinite number. We cannot show all the case. We cannot find a single contrapositive case in the infinite number of cases. It is almost impossible. So using this method, we can use induction. That will be much easier. So let's look at this. Yeah, induction is the rule of inference, right? It is only available for these natural numbers. So here we have the induction. The first P of 0 is true. Then for all k, P of k implies P of k plus 1 is true. Then for all n, P of n is true. So how can I apply this to prove a P of 5? The first, we have P0, that's true, correct? And we have this connection, P of 0 implies P of 1, that is true, correct? So that's why P of 1 is true. Next, we have another, now P of n is true, P of 1 is true, so we know P of 1 implies P of 2 is true. By the modus ponens, P of 2 is also true. Then we have to do other step. P of 2 implies P of 3 is true. Then P of 3 is true. Again, P of 3 is true implies P of 4 is true. That means P of 4 also true. Last step, P of 4 implies P of 5 is true. That's why P of 5 is true. It requires several steps, but we can generalize this using a variable k. So we need to prove P of 0 first, correct? Then we can assume there will be k, that is arbitrary integer greater than 0 and equal to 0. So we assume this is true, right? That is first step. Maybe if that is true, P of k plus 1 is our question. That is true or not. We know about that. P of k implies P of k plus 1 is true. If we can prove that P of k plus 1 is true, that means it shows that all the case is true. So let's look at it. So we have the rule of inference with induction. In this case, we need to find base case first. Then we have to uh, make this inductive hypothesis. We have to find k, and we have to set the k. K is the some arbitrary number, and we have to assume p of k is true, and we have to connect them with the implication over here. P of k implies p of k plus 1 is true. Okay, then we have to prove p of k plus 1 and the implication. Then, because of that, the general case, for all n, p of n will be true. Okay, let's look at this page. This one explains those equations in English. So first step I said that is uh, your question. So we will show that p of n is true for all the number of n that is greater than or equal to 0 by induction. That's right. We try to do this by induction. And next step, we have to find base case. Base case is p of 0. We need to show this is true or not first. So we prove this this uh, is true. Then the next step, we have to find inductive hypothesis. That is about the implication of p of k and p of k plus 1. So in this case, we assume the p of k is true. So next step, we need to connect p of k and p of k plus 1. So now we need to prove p of k plus 1 is true. If that is true, the implication is also true, and p of k as well as true. That means the p of n is true for all the case n. Uh, let's try to apply this induction for this simple example. This example is about the summation of all number from 1 to 2 to the nth. So when the n is 0, the result will be 1. That is n is 1, that will be 3, and it'll be n is 2, like here. Yep, this is 0, 1, 2, 3, 4. Yep. Yeah, it become larger and larger and larger, but anyway, it used several steps. So it has a general equation. So we can find the pattern from this. The pattern will be like this. So if we want to calculate that, we can simply use this equation instead of this complex computation. So from this, so you see 16 and 15, 18, 8 and 7, 4 and 3, 2 and 1. Yep. Yep. This pattern is true for this 4 case, but we have to generalize this pattern for all the case. So here we have problem. So left side and right side is equal. We have seen 4 cases, actually 5 cases. They are true, but we want to make sure this is true for all natural numbers. So yeah, we have seen this, the induction proof steps. We will use these steps to prove that. Yeah, first we have the problem. So we know P of n will be 1 plus 2 plus and go on, and 2 to the nth. That is equal to 2 to the n plus 1 minus 1. So we have the uh, problem, we have the equation we have to prove, and base case will be n equal to 0. Yeah, we have this left side, right side, and base case will be like this. So the right side will be 1 when the n is equal to 0. The right side will be like this, and this term will be 1. This is term will be 2 and minus 1. That also 1. So that's why base case will be true. We can apply induction hypothesis. So first, we suppose the P of k is true. So and then let's try to prove P of k plus 1 is also true. That will be like this, and this is k, P of k, and when we add 2 to the k plus 1 to both sides of P of k, that will be like this. Okay, so this left term is exactly same to the our assumption over here, and the right side will be like this. We can simplify that equation. That should be um, 2 to the k plus 2 for these two terms, because they are same, and that is 2 multiply 2 to the k plus 1, that is 2 to the k plus 2, and after that we can see the right side will be like this. This one is same to our assumption over there. So P of k plus 1 is same to P of k and plus 2 to the k plus 1. That means the implication is true, and P of k plus 1 is true. So P of k is true for all k by the induction. So now we have another example. This is a little bit complicated. We want to show 3 is the divisor of 2 to the 2n minus 1. And this is for all natural numbers. Okay, define the pattern. So the first step, 2 to the zeros minus 1. This will be 1, and minus 1 is 0, and 3 multiplies 0 will be 0. So that's why it's true. Next step, we want to add 2 to the 2 and -1, and the first term will be 4, -1, it will be 3, and right side 3 multiplied 1 is 3. That's true. Next one, yeah, 2 to the 2 multiply 2, yeah, that is 4, and 2 to the 4th minus 1 is will be like this. 16 minus 1 is 15. 3 multiplied 5. Next one, 2 to the 2 multiply 3, that is 6. So 2 to the 6th will be 64, and minus 1 is 63, and that is 3 multiplied 2, 21. Yeah, next one will be more difficult. 2 to the 8th minus 1 is 256 minus 1, that is 255. So yeah, this is a little bit complicated combination. 3 multiplied 85. But it is very difficult to find all the case. So we have to find the pattern. So 0, 1, 5, 21, 85. Okay, but that is really difficult. So instead of that, we can apply this induction. We know that 2 to the 2n's minus 1 is equal to 3k. The 3k means uh, k will be a divisor. So we need to find this k. Okay. Base case, when n is equal to 0, the left hand side will be 0, and right hand side 3k. 3k will be 0 when k is 0. So p of 0 is true. We know that the base case is true. So let's try to generalize this induction. Suppose p of k is true for all the case k, some k. So we want to connect this p of k and p of k plus 1. Note that uh, p 2 to the 2 multiplied k plus 1 minus 1 will be 2 to the k multiplied 2 square minus 1. By the induction hypothesis, 2 to the 2k minus 1 will be 3j for some j. So when you have p of k plus, that will be 2 to the 2 multiplied k plus 1 minus 1, and that will be written by this, and this part is same to the 2 2 to the k. So yeah, this will be here. We can move this term to this side, and that will be 3j plus 1 multiplies 2 square minus 1, and this will be like this, and we can associate with this 3, we can rewrite this to this. So again, the p of k plus 1 also a multiplication of 3. So it follows that there is some r that will be r is equal to 4j plus 1. This is some arbitrary number, and such that 2 to the 2 multiply k plus 1 is plus 1 minus 1 is another 3 multiplication. So that means p of k is true, p of k plus 1 is true, their implication is true, so that means the claim is true by the induction. Okay, we have another example here. So there is n is greater than equal to 1. The whole number less than n, we can some older number less than equal to n, that is same to n multiplies n plus 1 divided by 2. So we can rewrite this as this, that is p of n. So base case, when n is equal to 1, we can substitute n with this 1. The left hand side will be 1 because we have 1 in this case, 1 only in this case, as the order summation of order number is 1. So we can apply this 1 as here, 1, 1. This is 1, and this will be 2. Multiplication will be 2. We can divide by 2. That will be 1 again. So that's why p of n is true. Yeah. Now we can assume p of k is true for some case. Okay. This is the p of k. We want to improve p of k plus 1. So yeah, p of k plus 1 will be also like this, because p of k, and then next step we can add k plus 1 into p of k. That is so let's try they are same or not. So this is the p of k plus 1. So this is coming from the equation. If we rewrite this in simple case, so this part with same denominator 2 will be like this, and we can combine these two, k multiply k plus 1 and 2 multiply k plus 1. That will be this, k plus 1 multiply k plus 2, and this is same to this. So that means p of k plus 1 is true. So the claim is true for all n is greater than equal to 1 by induction. Yeah, next example is n to the nth is greater than equal to n factorial for all n is greater than equal to 1. Yeah, as you know, the factorial is the product of all the integer between 1 and n. So let's look at the claim. Yeah, P of n will be n to the n is greater than or equal to n factorial. We want to prove P of n for all the integer n is greater than or equal to 1. The best case is um, when n is 1. So 1 to the 1 to the first, 1 to the first is 1. And 1 factorial is 1. So the base case is true. Yeah, what is the induction hypothesis? Oh, we have P of k. That is true for some case. So we want to prove k plus 1 to the k plus 1s and k plus 1 factorial. By the induction hypothesis, k to the k is greater than or equal to k factorial for some k. So this will be true, and this part is same to this. We have seen this from the goal, that is P of k. P of k is so. Let's look at left hand side. Yeah, k to the k is greater than k plus 1 multiply k factorial. That so, but anyway, this part is smaller than our target. Um, so simply we can multiply that to the k plus 1 plus multiply k plus 1 to the k, and this will be like the k plus 1 to the k plus 1. So k plus 1 to the k plus 1 is greater than k factorial. So the P of k is true for all k when that is greater than or equal to 1 by induction. We can apply this method for this check for tiling. So um, so we have this tile, and we want to uh, make sure this can cover this 2 2 to the nth multiply 2 to the nth checkerboard without one square removed. So we can consider base case. So base case n will be 1, and 2 by 2 case, and 1 square missing. Okay, this will be a little bit different, but anyway, if that is like this, that is exactly the same. We can put this into this. So next step, we may have larger one. So let's look at it. This will be like this because it is based on 2 to the nth. Next step will be like that. But we have only one is missing. So here we can put a block. So let's look at. So this one also same shape. This one will be same shape. This one is same shape. And anyway, if there is one missing, we can put same thing, whatever. So we can keep doing this. This claim will be solved by the induction. Okay, we have discussed that induction in this case. So next class, we're gonna cover strong induction and reduction as well. Thank you.